Okay, I want to repeat everybody just to remind you, remember this video does go up on my YouTube channel. So if you don't want your whole name seen, make sure you change your username to just like your first name and maybe the first letter of your last name or something like that. And definitely let me know if that's a problem for you guys because, I'm going to put it up there and I'm not going to edit out anything unless you specifically tell me to. And if you do specifically tell me to, then I got to go figure out how to edit out those names because I don't really have any software to do it anymore. I bought Camtasia, but it stopped working when I got my new operating system, and they didn't offer any support for me. So, do any of you have speakers? I would like to hear someone's voice so that I could confirm that you can hear me, and then I could confirm that I can hear you as well.
We can hear you fine. Can you hear me?
Okay, cool. Thank you. Appreciate that. Yeah, I can. Thank you. All right. As is normally the case when I first come into class, I'm usually supposed to give you time to ask me questions about homeworks and stuff like that. I probably am, by the way, going to go ahead and push the homeworks back. I think I pushed them back till tonight, 11:59 p.m. If I can actually get on Pearson, which has been a problem, if I can actually get on there, I will push them back to tomorrow at 11:59. So just know that's your real due date, even if you can't get them. If we actually find out that there's a problem with Pearson, then I'm gonna have to give you more of an extension. But I do know for a fact I was having some serious problems with Pearson. Anybody else having problems with them? Like right now, when I click on Access Pearson, it gives me a 504 uh, delay or something error. And then if I click on an assignment, it gives me a 503, another error. So I'm not able to access the book or anything like that except for going through a back door. And you guys are not supposed to go through the back door. So I need to make sure they get this fixed. I've already submitted a ticket to both Canvas support, which is at our school, as well as Pearson support. I do suspect the problem should be on the Pearson side, but I'm not completely positive. So I've sent them to both of them. Can just give it a try, for instance, to check and see if you can. Yep, good. Okay. Yeah, I thought that was the case. It's not doing anything, so I really think it's something for the uh, shaking hands that's supposed to go on between Canvas and Pearson. So I did submit it. I was working with some reps there. They might have got a little ticked with me because I don't have time to spend with them, even though I wasted several hours trying to get them to contact me. They wouldn't. When they finally came back to me and got to me, the lady was super helpful, but she had to move it up to a higher level person, and that person didn't get back to me with a couple more days and wanted me to, do a bunch of stuff, and I just said, sorry, I don't have time. So I'm hoping that's not a vindictive thing against me and what I did, but we'll see. So it should be fixed by tomorrow morning. If it's not, then we're obviously going to give you a lot of extensions and stuff, and I apologize for that. What I will tell you though is if you can't do homeworks within, a few hours of covering material, like today we're covering material in this class. So if more than say 20 hours goes by and you haven't done a homework problem after seeing this presentation, then you need to go ahead and open up the textbook if you can get there, however, whatever way you possibly can, and try to solve some of the problems from the end of the chapter. Since that might be an issue, I will go ahead and take some pictures of the end of chapter problems and post those in our week 2 uh, module so that you guys can actually see some of those problems. And that's really what I mean is work like the odd ones because the odd ones have the answers in the back of the book. And that'll be plenty of practice for you to keep you fresh. I would say do the first 2 odd ones in every subsection at the end of the chapter. Once you've done those, that's pretty much close to equivalent to the homework assignment. It's a little bit less because the homework assignment has certain tutorials that I use to get some further teaching. But anyways, we'll look at it. I noticed the week 2 module isn't showing up anymore on can. Ooh. No, the week 2 module, I just put it back up a new version, so hopefully it'll come soon if it's not already. Thanks for asking me that, Chloe. Uh, okay, so Holden can get in, but Another person can't. Zachary couldn't get in. Yeah, well, that's hmm. Zachary, when you went in through Canvas. Holden, did you go in through Canvas as well? So Zachary did, and waiting for it. Oh, okay. Sorry, I misunderstood that. Oh, yep, I see a T there now. Sorry. The eyes are getting old because evidently some part of me is getting old. It's not me. I'm not getting older, but some part of me evidently is, I think. Oh, cool. It's back up for Chloe. Chloe, did you go in through Canvas or did you go in another way? Cool. Okay, so maybe whatever's happening might have got fixed. I hope that's the case. I've got it pulled up for us on this. Uh, Now, ideally, this scenario with chapter one is I'm not too worried right now about the relative reference frames and stuff like that. I'm going to cover that to some extent, but what I want to start off with is I'm trying to use your second lab, which is the motion detector lab. I'm trying to use that and your understanding of that lab, which if you've had it before, if you've already had that lab, then you're ahead of the game and that's great. If you haven't, you're a little bit behind of the game, but it's still going to be good for you because when you get to the lab, that'll be easier. Whereas if you'd had the lab first, this would be easier. So I think both of them will help you. But I'm going to use that to sort of motivate some big facts that my students just aren't getting nearly every semester. I haven't, I have a handful that always gets it, but there's a majority of the class that doesn't get certain things. So I'm trying a different way. What I'd like to do is I'm going to go ahead and share my screen with you. I'm specifically going to share a screen from Excel. Uh, what I've done is I made a position versus time graph in Excel that I want to analyze in terms of everyday, life and stuff, and try to get some motivation or give you some motivation to come up with the discovery that we need to understand some of the material that's going to happen. So let's go ahead and open up my Excel window, and it looks like there it is. So I'm going to share this window. That should pop up in about a second. Okay, there it is. Now, this window is not huge, obviously, so that's a little bit of an issue all by itself. But there's other graphs in there too. I want you to ignore those other two graphs. We're looking at graph one right now. So this is the data from graph one. This is the data from graph two. This is data from graph three. That's not necessarily important. What I want you guys to see is this. We're imagining a scenario where maybe I look out into my front yard or the road out in front of my house, and I'm just going to put a mark in the road, and I'm going to call that the origin of a number line. And I'm going to say, right there's that dot. I'm looking at it right now. And I will go to the right. And at 1 meter away from that dot, I'm going to put a one. And at 2 meters away from that dot, again, going parallel to the road, I'm going to put another uh, hash mark and put a two for 2 meters and then 3 meters, so on and so forth. And in fact, I'll go to the left and put a -1 meter and a -2 meter and so on and so forth. Now that we did that, we have what we're studying in this chapter one, which is basically one-dimensional motion. And one-dimensional motion is nice because there's very little difference between scalars and vectors when you're dealing with one dimension. And we're going to cover vectors in chapter three. And we need to have some understanding of motion, position, velocity, acceleration, those types of things. We need to have some understanding of that before we go into vectors. And that's what we're trying to get. So what I'm going to try to do is focus on this graph one here. So everybody sees that. I'm going to make it as big as I can real quick. And I want you, well, hopefully that should cover up the other ones, but it's being either very slow or not doing it. I don't know. Okay. Okay, let me try move. I'm going to try to make this window a little bigger and then move the other graph from behind it. So hopefully that wouldn't be a problem. I'm gonna put it right over here. So that's almost not a problem. Still working on it. Hold on, folks. Okay, got that one out of the way. And now I'm going to get this one. Oops. Undo that. Get this one, move it out of the way. Okay. Now, what I want you to see is this axis right here is obviously the x measured in meters, and then the x-axis is actually time measured in seconds. Okay, part of this is me trying to remind you that when you have something versus something, the first word, the word that precedes the word versus, that's supposed to be your vertical axis, and that's supposed to be your dependent variable. Okay. The thing that comes after the versus, VERSUS, is the horizontal axis, and that's supposed to be the independent variable. So those are words you need to know and get used to just in terms of everyday life and the mathematics that's going to follow you because you've chosen a career in the physical sciences or engineering. Now, what I want you to do is notice at t equals 0 seconds, which is this little zero right here. And remember, t is the horizontal axis. So everything that corresponds to t equals 0 is everything along this vertical line right here. That is our x-axis. Okay. X in meters axis, the vertical one. Okay. That's a problem with this is we are using X to correspond to distance. And you could use D, which is what the manual uses, our labs use on the lab, but I used X. Now, if you look at this data point says it has a position that is X, the horizontal axis has a value of 0 and the vertical axis has a value of 1. So what that means is at t equals 0, the person was 1 meter to the right of my origin that I imagined drawing out there in the road in front of my house. Okay. Now, here's the neat part. What I'm going to do is I'm going to go from that t equals 0 seconds to t equals 2 seconds. And we're going to have yet another data point. We can see that this data point corresponds to 2 seconds, and it also corresponds to 5 meters. So that's something kind of big. And I think I have some ability to write on this screen. Here it is, annotate. So this point right here, that point is parenthesis, and this is not going to be pretty because I'm doing it with my mouse pad, so you can imagine it's going to be pretty ugly. But that's going to be 0 seconds, comma, 1 meter, and I'll put the meter on here just so we'll remember how bad I wrote a meter, I guess. Just so we'll remember that that second data point is the actual vertical axis, and that's measured in meters. Okay. Now we have up here another data point, and this time it is t equals 2 seconds, which I can put an S. Whoa, Nelly, that was really bad. Ooh, and I don't immediately have a way to undo it. So there's probably an eraser somewhere. Let's check this out. Annotate. Well, oh, there's my tool. Okay. Yeah, I do have a toolbar here. So now I just got to find the eraser. There we go. Okay, that was really good. Okay. I did not know it was going to be this awful, but yay for us. So this is 2. And then that's seconds, of course. And then comma, we see the distance is 5 meters there. Okay, so I'm sorry about how horrible that meter looks, but this is this is what I'm having to deal with. So I wanted to mention something. So from t equals 0 seconds to t equals 2 seconds, I've went from x equals 1 meter to x equals 5 meters. So how much distance have I traveled in meters? You probably all know how to do that, right? And feel free to answer in the chat or just speak out loud. That's okay too. Whoa, Nelly. I just wrote on something by accident. Let's see if I can first put this over here. And second, I'm going to do undo. Okay, so did anybody give me an answer for what they thought was how far we moved? Yes, Holden did. So yes, we moved 4 meters because we could do 5 meters minus 1 meter to get the distance. So that tells us something. That tells us the vertical axis or the vertical dimension is a measure of distance in meters. So when I look up here at this point, 2 seconds, 5 meters, that tells me, since the 5 meter part, that tells me the height of that dot is 5 meters above the horizontal axis. And that also tells me that's the distance that I am or something is at t equals 2 seconds. Now, in the interim, going from 0 seconds to 2 seconds, I went from 1 meter to 5 meters. So I found, in fact, that the rise, oops, that was supposed to be a pencil mark that didn't happen. So this right here is my rise, and this right here is my run. So the rise is 5 minus 1 equals 4 meters. Okay. And the run, of course, is just 2 minus 0. So run. And notice I'm doing rightmost point minus leftmost point. As long as you do the consistent order in the top and bottom, you always get the right answer. So I could do the leftmost minus the rightmost, and that would give me exactly the negative of what I got for the rise. But then I'm going to do the leftmost minus rightmost on the bottom. That would also give me the negative of what I did on the run, and the two negatives would cancel out. So in this case, we get run, and now you have some understanding of how you can do it in either order. Doesn't really matter. But in this case, it's going to be 2 seconds minus 1 second, which gives me 1 second. Now, what we discovered is that I went from 1 meter to 5 meters in a time of 2 seconds. Oops, 2 minus 1 is 1. Yeah, that makes sense. Okay. And therefore, my distance traveled was, in fact, 4 meters. So, does anybody have any idea roughly what speed I was traveling at as I went from 0 meters to the 5 meter mark? Or specifically, I went from 1 meter at 0 seconds to 5 meters at 2 seconds. Anybody have an idea what my velocity might be or speed? Oh, thank you. 2 minus 0. Yep, that's the problem. Thank you. Holden caught me on that. Yeah, good job. I did 2 minus 1 because I saw the 1 meter instead of 2 minus 2, instead of 2 minus 0. So yeah, that was a boneheaded thing to do. These these crappy numbers have gotten me kind of discombobulated, obviously. All right, now back here. So it's 2 seconds minus 0 seconds. Thanks again, Holden, for that. And this time it's going to be, that's supposed to be a 2. I know that's horrible. And I could probably type it, but it'd probably take so long to type it. I'm not bothering to do that. So let me try and see if I can do it a little bit better. Well, I can erase it a lot better, that's for sure. Okay, so 2 seconds is the time and 4 meters is the distance. And Chloe says, as well as Charles says, that my velocity is 2 meters per second. And that's exactly right. But that also happens to be our slope. So you have to wonder, is the slope something related to the speed? And in fact, if you go up here, you can see that the slope is the same all along here. So if we are making the conclusion that our slope is our speed, then a line with a constant slope is traveling with a constant speed. But as we learn, especially in chapter 3, if this line went from the top left of the graph down to the bottom right, then it would be leaning like this instead of like that. This line, which leans like the one on the screen, is a line that has a positive slope, whereas this line is a line that has a negative slope. So you might actually realize that, hey, a positive slope means I'm going in the positive direction, and a negative slope might even suggest I'm going in the negative direction. For instance, if this was the point at which I was at t equals 0, and this was the point at which I was at t equal 1 second, then I would obviously get a run that is negative, and then I'd get a rise that is negative. And of course, the negative divided by the negative is still going to give me a positive. But we're going to have, in that case, because we flip it around, it would actually give us a negative slope. So we might be thinking that. The big thing that I'm trying to take here is that I'm trying to figure out if it's normal to have a slope look like a speed. So now that we have that work done, let's look at this other graph, which is a graph of position versus time, but this time it's not a straight line. So we, had those marks there. That explained something about that. What I want to do now is look at this one. And again, in this case, I've got at 0 seconds, this is actually going to be 1 meter of height, or actually, I think I did it 2 meters. In fact, if we check the data, you can see at time t equals 0, the position was 2 meters. And then at 1 second, it was 4.5. At 2, it was 10. At 3 is 18.5, so on and so forth. Now, this one's not a straight line. So if we really are finding that the slope is somehow related to a speed, then this one should also give something consistent with that. So for starters, is the slope from the first data point to the second data point, is the slope between those 2 points smaller than the slope, let's say, between the last 2 points? Yeah, so this graph, if we're really thinking slope is velocity, this graph should be suggesting that something was going fairly slow for the first 1 second and fairly fast for the last 1 second. And in fact, it won't be accurate because this is a curve here, but if we just drew a line that connected the first dot with the second dot and found the slope of that, that would be in some sense a rough estimate of how fast it was going. Again, assuming that we were right the last time with the slope being the velocity. In this case, we'd say the slope is sort of the average velocity, maybe, because we know if we took the slope at this particular point, it would be one thing. If we took the slope at this particular point, it would be another thing. In fact, we know from calculus that if you want to find the slope at a particular point, you draw a tangent line and then you figure out the slope of that graph. So if I wanted to know, for instance, the velocity as slope, again, assuming its slope is the velocity, if I wanted to know it for this particular data point, I would draw a tangent line right there, which that looks almost nothing like a tangent line, which is exactly what I had planned, not really. Okay. But the main thing is, I think you see that I was trying to draw a line that was specifically parallel to that data point at that data point. Then if I did rise over run for that, again, imagining perfectly straight lines that your instructor was not a moron and actually did. Okay. If you do that, rise over run does give you something that notice has units. Rise has units of meters and run has units of seconds because it's over here. So it does actually have the right units, just like this one did. And it does have the property that over here, the slope is steep, and over here, the slope is shallow. So if I tried to do, for instance, a tangential line there, it would maybe be at this angle. Again, that's a horrible tangent line, but I think you get what I'm trying to say. It'd be much better to just draw a line and adjust it to the right parameters. That didn't seem to be what happened there, so we'll just go with it as it is. But the main thing is right here we see that we have a different slope. So let's look at it and see what's actually going on and see if this is consistent with the slope being the velocity. So for instance, right here I have a position of, well, let me find out. For starters, we can actually go to our graph, and that's time t equal 1 second. It looks like I can't go to the graph until I switch my tools I'm using. But at t equal 1 second, I've got the position being 4.5. So I'm going to say one. Whoa, Nelly. I got to put back to the drawing. So I'm going to say 1, comma, 4 point, oops, I'm actually doing that. No, I'm doing that right. 4.5. Okay, that's that first data point. Now, let's go to the second data point, which is 2 and then something. So that one is 2 and 10. So the other data point is going to be 2 seconds and 10 meters. So in that 1 second between the first, or actually technically the second data point and the third, there was 1 second between those two data points, and I went from 4.5 meters to 10 meters. So the distance traveled would be 10 minus 4.5, that's 5.5, and the time taken would in fact be 1 second. So roughly, can anybody give me an idea of what that speed is? Ah, Daniel's asking, can you find the instantaneous slope at a point without the equation x of t? Yes. If you actually have enough data points, you can. And that's sort of where I'm going. So good question. Anybody have an idea what you think just a ballpark figure of the speed would be between the 1 second and the 2 second data point? Has anybody ever tried to think about how fast? There you go. Good job, Daniel. When you're actually on a trip, sometimes you use your odometer or your trip meter on your car, and you can keep track of how far you've driven, and then you can also keep track of what time you left versus what time it is now. And that allows you a way to come up with something like an average speed. And that average speed can be super valuable. For instance, if you keep track of that on a trip, let's say you're going to vacation at Disney World, then you can keep track of your trip all the way from, Virginia Beach to Disney World. And when you do that, you'll get an average velocity for the whole trip. Now, if you cut out, bathroom breaks and food breaks and all that stuff, then you'd get a rough estimate of how fast you were going on average the whole trip. But if you leave those in, that'll give you more of a measure of how long a trip would take that includes the typical need to take breaks for bathroom and food and stuff like that. So both of those values can be very valuable. It's just a matter of which one you want. But I keep both of them when I'm running trips, and my wife is constantly, kind of getting on me about it because I'm a horrible driver, but it's mostly because I'm, paying a lot of attention to doing calculations instead of as much attention to the road. So that's kind of a dangerous thing. But if you actually had those odometer readings and you had how long you were on the road, does anybody know how they would calculate maybe what their speed was on average? You can speak it up or you can type it out. It'd probably be easier to speak this one.
You
So
just mean distance over time?
exactly. So, and this is a key thing that I want you to understand. Terry Pratchett, for instance, a great author who passed away a few years ago, would always make these arguments in his books about narrative and narrativium. He actually like acted like there was an element called narrativium or something like that. But the point was that if you have a story that you can internalize and make sense of, and that leads you to certain conclusions, then you're not going to lose those conclusions like you would just someone telling you a list of facts. So, for instance, I want you to think about when you're in physics, I want you to think about how similar this is to what you do in everyday life, not focus on how different it is. So, for instance, when I didn't catch which young lady said that, was that Chloe that was speaking earlier? So if it was Chloe or Daniel here, yeah, it was, thank you. And Daniel here also typed it. When you look at your speedometer, that's a key to physics. You look at your speedometer and it says right there, MPH. And what does MPH mean? It does mean miles per hour. And I want you to think about this for the rest of your life as a engineer or scientist or whatever. When you see the word per, in problems or in situations where someone gives you a story or something like that, and you're trying to figure out something physical about it, and it requires some math, I want you to think of the word per as if it is a division symbol. So when you see miles per hour, I want you to immediately think distance divided by time because mile is a unit of distance and hour is a unit of time. So distance divided by time is in some sense an average speed. And that's exactly what we're getting at here. I'm showing you that these slopes tend to be something like the speed, and these slopes turn out to be something like an average speed, especially for this curved one. So, for instance, this curved one, we went a distance of 5.5 meters, but in a time of 1 second. So, the average speed, which you'd write it as S, but you put a bar over it to represent average. Of course, you can also put it in these greater than and less than brackets. That's another way to write average. I'm sorry that my S's are looking like fives. I'm doing my best. But anyways, that's an average speed, and it really is distance divided by time. Okay. So we got, in this case, between these first two data points, 5.5 was the distance traveled. And then that was divided by 1 second. So we got, oh, that was really bad. That looked horrible. Ooh. So we got 5.5 meters per second. Okay. Now that's a pretty good speed. For instance, basically 1 meter per second is about 2.23 miles per hour. So 5.5 is, pretty dang close to 15 miles per hour. But if we came up here and inspected these 2 points, which we can, let me change my stuff again. Those very last 2 points are 106, 82.5. So 106 and 82.5 are the two distances. So when I go to do that, I can say, okay, in this case, let's write the actual thing. This has a time of 8 seconds. So I'm going to build a snowman, bad one, and it's 106 meters for that guy. And this one, on the other hand, is 7. And we decided the graph was it 86? Let's check that. Uh, 82.5. That's what it was. Okay. And you get this back where I was. Okay. Like that. So now 82.5, the 8 is the worst of all numbers to make so far. Well, the decimal is really problematic too. But anyways, so 82.5, that's not a great data point, but still the main thing, or that's not great writing, let's put it that way. So in this case, I'm going to do 106 minus 82.5. So when I do this, I say 106 minus 82.5, and that gives me 23.5 meters. So I'm going to say if this is really the average speed, then the average speed is coming up to 23.5 meters. And then, of course, that's between 7 seconds and 8 seconds. So that's divided by 1 second. So this is 23.5 meters per second compared to 5.5 down there. Now, we did realize that the slope does seem to look like a velocity. It has the units of velocity or speed, and the steepness does seem to be increasing here. That's consistent with the slope going up. And we just calculated that the speed, if this really is a formula for average speed, the speed here is 23.5 meters per second, and the speed here was 5.5 meters per second. So the fact that this is more gradual and that's more steep tells us that, yeah, this is behaving like a velocity. And in fact, what we've discovered is that velocity is the derivative of position versus time. So we can say, for instance, velocity, whoa, we can say this with something else other than this language. I will come back to this graph in a second. Let's stop sharing that and let's turn on my iPad now. So I'm going to share my iPad. It should come up any second now. So the conclusions that we've reached so far is that the average speed, I don't think I want to write in red right off the bat, the average speed, which could be written that way, or it could be written, well, actually not that line up there, or it could be written this way, is average speed, and that's distance traveled divided by time taken. Okay. Now that's what we hinted at, thinking that this was actually the an estimate of the average speed based on our idea that the speedometer said miles per hour. So that was all because mph means miles per hour, which means miles. Now, remember, a fraction is basically just a suspended division. So I can do a fraction bar and write this as miles over hours. And then everybody realizes, oh, I'm dividing the miles by the hours. So from that, we've got an idea of average speed. And now what we realized is that the slope of x of t versus t is, we normally use the symbol m for slope. So I'll write m, and we say rise over run. And that, of course, would mean x final minus x initial, which you can write as an I or a subscript 0 or whatever, doesn't matter too much. And then the run would be t final minus t initial. Okay. So that's the way we calculate slope. And in fact, from 1 second to 2 seconds, we had m equals 10.0 meters minus 4.5 meters divided by 2.0 seconds minus 1.0 seconds gives us 5.5. I'll just leave that as meters on top, divided by 1.0 seconds. So that gave us our 5.5 meters per second. Now, when we did that with that completely straight line, the first one, the graph one, then the actual slope was the actual change in velocities. When we did it on the curved one, though, we were sort of estimating because what we were really doing was, and I'm going to try to draw it a lot more curved than it really was. But for instance, we could have had these 2 points, and this one would say correspond to 1 second, and this one would say correspond to 2 seconds. And what we're going to do is imagine that that is the actual line connecting them, because then when you do that, this is the rise and this is the run. And you can see it's not exactly the right answer, right? Because exactly the right answer would mean that this line should lay exactly on the curve. It doesn't. That blue line is slightly different. What you'd want to do is, if you want to know the velocity at 1 second, you would try, let's zoom in on this a little bit. So actually, let me zoom in on a little bit this way. I'm going to put that one here, and I'm going to put this one here, and I'm going to show the curve like this. And then I'm going to show the line, straight line like that. Again, this part is going to correspond to 1.0 seconds. And this part is going to correspond to 2.0 seconds. Okay. Now, if you wanted to know the speed at the actual 1.0 seconds, then what you'd really want is a tangent line. And a tangent line is supposed to be just parallel at that particular location. I think that looks like a lot better tangent line, obviously, than the ones I drew before. But now you could, in fact, get a whole new rise over run. Okay. And that one would be completely accurate for the velocity at t equals 1 second. So this m is an accurate calculation of the speed at t equals 1.0 second, because I drew a tangent line at the t equals 1.0 second, and then I calculated that slope. Okay. The way we would go about doing that, though, is we would say, okay, well, t is equal to 1.0 seconds, and then what I'm going to call this is delta t. And obviously, t plus delta t in the initial case gives me a whole second. But if I imagined making it, let's say, just a little smaller delta t, then we might get one line that goes like this, and that would correspond to a different delta t. And then we could go a little smaller still, and that would be a different delta t. Maybe that's delta t2. But if we kept doing that, getting smaller and smaller and smaller, these lines, which are called secant lines, these lines would slowly morph into the tangent line. So what conclusion we reached is v at t equals 1.0 second is equal to something we call the instantaneous velocity or speed. Again, in chapter one, we're using the words velocity and speed interchangeably. Uh, this will be called the instantaneous velocity, and it's actually equal to v instantaneous is basically calculating delta x over delta t. And remember, whenever you see this symbol right here with a variable after it, this is defined to be the final of that variable minus the initial of that variable. That's always what the delta means. If it means anything else, whoever's giving it to you has to tell you that that delta means something else. Otherwise, you just always assume it means change in, and it's the final of the variable that follows it minus the initial of the variable that follows it. So this delta x over delta t, which is very much the definition of rise being delta x and run being delta t, but we're taking the limit as delta t approaches zero, which means that this v instantaneous is dx dt. And specifically, we're evaluating at t equals zero, or excuse me, at t equal 1.0 seconds. Okay. So what we have here is a new idea. This is average speed. Average velocity, on the other hand, is equal to delta x over delta t, which would be x final minus x initial over t final minus t initial. Notice that's a little bit different than what we wrote on the average speed. The average speed was found by basically taking your odometer reading or your trip meter reading and taking how exactly how much you moved, not the difference in where you are and where you were, but the actual distance traveled from where you were to where you are. So, for instance, you could go in, if you have a circular driveway, you could drive around your driveway 1,000 times, and it might read 100 miles when you're done, but you're literally parked in the exact same spot that you were before you started moving. In which case, the average velocity would be x final minus x initial, but x final and x initial are the same thing. So you'd get a zero average velocity, but your average speed would be, 100 or so miles divided by the hour you actually traveled. Okay. So that's the big difference. And then now we have this additional fact that is the instantaneous velocity has to be equal to the time rate of change of delta x over delta t, which we get by taking the limit as delta t approaches zero. That's all part of a bigger picture that we're supposed to see. So what we found is that we can have x of t, which is a position, as a function of time. Okay. Now, notice I said function of time. A function, remember, is something that has to pass the vertical line test. uh, you would imagine that a physical object would need to pass the vertical line test, because the vertical line test, if you fail it, what happens is that you've got two different vertical axis values that correspond to a particular time. So that meant you're at two places at once. That's not possible. So function of time is a good thing. When we use the word function, that's a good criteria for a physical object. So position as a function of time is a basically another word for trajectory or the path on which you're traveling. But you can get to v of t, which is the velocity as a function of time by a mathematical operation, and that mathematical operation is a derivative. Okay. So if you're lucky enough for someone to give you a x of t type function, you can go ahead and use that to find out a v of t type function for the velocity as a function of time, and that'll make a velocity as a function of time graph. And all you have to do is take the derivative of it. Similarly, if I can stop for just a second and look back at our other graph, I'm going back to my Excel. Now, in this case, I'm dealing with graph three, and that graph three is meters per second versus time in seconds. Now, what this means is, for instance, this little data point, that one seems to correspond to 1 comma 4. So that is t equals 1 second, v equals 4 meters per second. So I can do this again. Let's get up here and get my little markers. Any old day now would be great. Okay, there you go. So I can say 1, 4, and the 4 is in meters per second, which is horribly written, but I think you get the point. Okay. And now if I look over here at this data point, let me kill this thing again here. Let's take this. Oh, let's just take this other one. Oh, that might not have been right, whatever I was taking. That one was definitely right. This is definitely 2 seconds. Okay, this one's definitely 2 seconds. I'm leaning towards thinking that might be 7, but I'm going to check my data just to find out. So at 2 seconds, yes, we have a distance of 7, or a y-axis of 7. So that's our data point there. Our other one is, I'm going to write it now. The other one is 2 seconds, comma, 7 meters per second. Okay. So if you just look at those two data points, you'd say, okay, from the 1 second mark to the 2 second mark, I went from going 4 meters per second to 7 meters per second. How much did my velocity change during that time? Feel free to speak it out. So when I ask you how much the velocity changed, that just means a simple subtraction. So we're going to do 7 meters per second minus 4 meters per second. So I can see what happened here is I had a rise that was 3 meters per second, but I had a run that was just 1 second. Now, in this case, meters per second is your change in the top, and then you're dividing it by the time. That sounds a lot to me like the 0 to 60 in 4 seconds. And when someone says 0 to 60 in such and such a time, they're telling you about a car's ability to take off and speed up to 60 miles per hour. If you need to pull out into a 55-mile-an-hour zone without getting hit by a car, you would really like to be able to go from 0 to 55 or even 60 miles per hour in a very small amount of time so that people won't bang into you from the rear end. and you won't have to wait a long time. So if you have a car that's good at that, then that car would be said to have a lot of acceleration. And a good measure of that is how long it takes you to get from 0 to 60. If it only takes you 4 seconds, then literally, as long as you've got 4 seconds for yourself to pull out in front of that car and get out of the way, then 4 seconds is enough to keep you from getting hit. And since you're going from 0 to 60, if the car is actually minding the speed limit, going, 55, roughly 60 maybe, then you can pull out in front of them in principle and not get hit. So that's the purpose of the 0 to 60, is it conveys to us a measure of acceleration. And when you say 0 to 60 in 4 seconds, you could literally take the 60 final velocity, which is in miles per hour, minus the 0 initial velocity in miles per hour. When you subtract those, you get 60 miles per hour. And then you're going to divide it by the change in time, which is 4 seconds. If you divide 60 by 4, that comes up to be 15. So you're getting 15 miles per hour every second, or 15 miles per hour per second. That's what we're looking at here, is we're looking at 3 meters per second per second. And that is acceleration. And now we can say that just like going from x of t to v of t required a derivative, going from v of t to a of t requires a derivative as well. Okay. So I'm going to kill this now. We have a little bit more of an understanding in some sense of exactly what this is. So now I can make yet another statement. I'm going to turn on my iPad again. Well, I think I'm going to keep turning it off like a goober. Okay. So we just found that x of t can go to v of t through a derivative d by dt. And I just argued to you that v of t can go to a of t by d by dt. So what we did learn was speed average, which also equals speed in here, is distance traveled divided by time taken. Okay. And average velocity is x final minus x initial divided by t final minus t initial. And I want to reiterate that this is uh, something we call displacement. And that actually turns out to be a vector quantity divided by time elapsed. So that's our average velocity. This is our average speed. And this displacement means it's literally a difference in positions, x final minus x initial. So you can see that they're necessarily going to come up different from the average speed. And now that we've discovered this neat new fact, we can also say that v of t is actually equal to the limit as delta t approaches 0 of delta x over delta t, which is what we call dx over dt. So that's a new equation. And now we also discovered that a of t, which on average, actually, let's do it that way. Let's get rid of the a of t first. Let's talk about the average velocity, or the average acceleration. That's equal to v final minus v initial over t final minus t initial, which was actually the slopes that we were calculating a second ago, right? That's all we were doing, was taking the v final minus the v initial and all that sort of stuff. So it does stand to reason that the average acceleration should be this. And now we can go one step further, By analogy, it makes sense that the instantaneous acceleration should be a limit as delta t approaches zero of delta v over delta t, which is, of course, dv dt. But you can also write that as d2x over dt squared. So we've got some pretty big stuff, and we can represent this most simply by doing this. And all we have to do is say, now, just from your knowledge of calculus, can anybody imagine what we have to do to go from right to left instead of from left to right? Integrate. Very good. It took me a little while to find the comment section, so the chat. But yeah, the integral of a of t dt would get you to the v of t, and the integral of v of t dt would get you to the x of t. So all of that is a really big concept for kinematics and physics in general. Now that we have that, what we want to do is kind of find an equation for a certain select set of problems. And the certain select set of problems is this. Imagine, whoa, focusing on only problems where the acceleration is a constant. So a of t equals a, which is just a constant. Okay. Well, from the above, we've learned that a is actually equal to dv dt, which means we have what's called a differential equation. This is a first order differential equation, and it's really a simple one. And there's a couple ways you can do it. And I'm showing you how to do it, and we're going to use it to get results, but we're also going to expect you to understand how to do this because I can give you an acceleration that's not a function of time, I mean, that's not a constant, and you're going to do the same process to figure out what the velocity as a function of time is, and then the same process again to find out what the position as a function of time is. So this is definitely a skill you need to learn. So what I'm going to do first is I'm going to realize that I'm working with an equation, and as long as whatever I do to one side, I do to the other, again, barring multiplying through by negatives or dividing through by negatives, then it should remain a valid equation. So what I'm going to do is I'm going to take both sides and multiply them by dt. Now, that might bother you. I know it bothered me because every now and then I would see my calculus teacher doing things like he was treating the dVdt, which I treated as a symbol for derivative. He was like separating it and put the dv over here. And I'm like, you can't do that. Those are just parts of a symbol. Well, it turns out they're actually things, and those things are called differential forms. They're actually specifically called a one form. So if you were fortunate enough to be at like a Princeton or a Oxford or a Cambridge or something like that, their Calc 3 course might cover this. Generally, we don't get to do that, but you could, in principle, learn it as a Calc 3 thing, but those things are called one forms, and they're just like vectors, but they're sort of the opposite side of the same coin as a vector. I'll leave it at that. Now that I have this equation, I've multiplied by through by dt, and now I'm going to integrate both sides. Now integrate, we didn't learn about that in algebra as being something that you could do to both sides of the equation, as long as you did it to both sides. But we had learned in calculus that an integration really is just a sum. You're just adding up, in this case, an infinity of things, but you're still just adding stuff. So it seems reasonable that you could integrate both sides without messing up the function. Now, I'm going to integrate this without a limit of integration. I've done it in other videos where I do the limit of integration, but I like doing it this way, so we'll do it right now. Uh, First off, the fundamental theorem of calculus tells us that the right-hand side, the integral of dv dt times dt, that should just be v of t. Okay, that's what the fundamental theorem of calculus is. It basically says, hey, not only is a derivative the tool that we use to find the slope of a line at a point, and not only is the integral what we use to find the area under a curve, but it turns out those two operations are inverses of one another. So one undoes the other. And that's what we're seeing here is I have a derivative that's doing differentiation, and then I have a integral that's doing integration, and integration with differentiation gives you the original thing, which in this case is v. So what I'm going to get is the integral of the constant a is just a times t, but there's no limit of integration, so no ranges that I use, so I have to add a integration constant. And technically, I would add one for this side too, but you could just make both of them the sum and call that C. But the main thing is what we'd get is V, which I'm sort of tempted to write as V of t, because that's really what it is. We have V as a function of time, but it makes it the notation a little ugly, so I'm not going to mess with it. Now, if we assume that V of t equals V0 at t equals 0, then we get this result. We get specifically a times 0 plus c equals 0, or excuse me, equals V0, like that. So we now know what C is, and that tells us specifically that V is equal to V0 plus AT. And if you look at that, that actually turns out to be the same thing as the average acceleration. Okay, so we found an equation, but it turns out to be one we already knew, but that's okay, because now we can also make use of the fact that V of t is actually equal to dx dt. So that means V0 plus AT is equal to dx dt. So we should be able to, again, do exactly the same thing we did last time. I'm going to multiply both sides of the equation by dt, and then I'm going to integrate. And actually, I probably should have done a little bit more room here, so I'm going to fix that up a little bit. So a of V0 plus AT, all of that times dt. And then on the other side, I get the integral dx dt times dt. So this is going to give me 1/2 AT squared, because that's the integral of a times t, plus V0t, but we are integrating without limits of integration, so I have to add a plus c, and the other side is just going to be x. Again, I hesitate to write it this way because it's ugly, but technically speaking, it is x of t. Now we assume that at t equals 0, x of t is equal to x0. So now we get that 0 plus c is equal to x0. And we see that the c is equal to x0, and we get a new equation. And that new equation is x is equal to 1 half a t squared plus v0t plus x0. That's our new kinematic equation. Okay. Now, there's one more thing I want to do, and that is, what if I wanted to use this equation, this x equation, and maybe I wanted to be able to find velocities, but I didn't want to have to know the time. Well, could we find such an equation? Well, we can. To eliminate the time variable, we can use v of t, or excuse me, we can use v equals v0 plus at to replace t with, whoa, that was bad, with t equals v minus v0 over a. So when I do that, I get x. I'm going to subtract the x0 from both sides already, so I'll do x minus x0. I have the 1 half a. Now I have the t squared, so that's going to be v minus v0 over a. That quantity will be squared, plus v0. Now this time I just have t, so it's going to be v minus v0 over a. I'm going to go ahead and square that. I'm going to call this a over 2. And I'm going to call this down here a squared. But I have a binomial that is squared in the top. Therefore, I have v squared minus 2v v0 plus v0 squared. That's what you get when you square that binomial. Plus, now I'm going to multiply that v0 through in the numerator. That's going to give me v0 minus v0 squared over a. Now I can see that this exponent of 2 is going to cancel out that one. And in fact, to get a common denominator, I need to multiply by 2 over 2. So if I do that, then what I'm going to have is v squared minus 2v v0 plus v0 squared. All of that will be over 2a. And then this one's going to be 2v v0 minus 2v0 squared over 2a. They're clearly fractions that have the same denominator. So now I can write v squared minus 2v v0 plus v0 squared plus 2v v0 minus 2v0 squared, all that over 2a. And what we can see is this minus 2v v0 added to 2v v0 gives me 0. And in fact, the result is v squared minus v0 squared over 2a. So we can finally say, well, I won't say finally yet, v squared minus v0 squared is equal to 2a x minus x0. And now I'm going to put it in the form that you might have seen before, and that is v squared is equal to v0 squared plus 2 times a times x minus x0. So this is a new kinematic equation as well. and it requires A equals a constant. This one requires A equals a constant. And this one requires A bar R, A equals a constant. Okay. But those are our kinematic equations. And that process I just went through, starting with the acceleration, which could actually be a function of time, and setting that equal to dv dt like I did in this particular spot right here. Okay. I integrated that and then use some initial conditions to evaluate that. In the problems that your book will give you or that the online homework system will give you, they'll give you very specific stuff like at t equals 0, the velocity is 3 meters per second. So at this point, you don't have to make up an assumption. You'd actually be given it, and that would get you velocity as a function of time. And then, of course, you use this expression to get the next level. And again, you'd have another initial condition that you could fill in until ultimately you get something like this trajectory for any acceleration as a function of time. So you do actually have to do that. You'll see some examples in your homework, or specifically, I know you'll run into quite a few in the practice test. Uh, so that's all I wanted to get done for right now. Next time I'll talk about, moving reference frames, which is what your chapter starts off with. I'll show you more examples with this. I'll show you examples like giving A that's not a constant. How do you integrate that to find the position as a function of time? I'll do that stuff. But the big thing I wanted to mention is because we missed last week, in principle, I'm moving all the homeworks back, and that's probably going to require, other than those last tests, it's also going to require me to push the test back. So your tests were supposed to be due like on January 2nd, your first online test. I'm pushing that back to January, or excuse me, to February 2nd. I'm pushing it back to February 9. So that's when your online test will be due. I'm putting the practice test up now. You will have all this time to work it. And then basically, when I put the actual test up, you'll have until 2/9 to turn that in. Or to get a grade that you like and are content with. So that should become available really soon, if not immediately. So you guys are free to go. Go ahead and chat me your first and last name so I'll have that for roll. And you're free to go, and I'll wait for the last person to leave in case anybody has any questions. Oh, yeah, one more thing. I have several students that haven't turned in the cut and paste thing from the syllabus. You're supposed to have that done in the last class day of January. I think I said like 29th or 28th or something like that. So make sure you get that done. Uh, And I think, oh yeah, also, if you include a photo in your SIS file, like when you first try to go into my TCC, you get the arrow or the area where there's a Canvas link and there's a SIS link. If you put your picture in there of your face so that I can actually see your face, that'll help me better learn your names. And I'm giving you 3 points on your first face-to-face test for anybody that does that. If you already have it done, I'm going to give you 3 points anyways. Okay. So that's something I want all of you guys to do for me so I can work on learning your names. Even though you're my internet students and I don't get to see you that often, I'd still like to learn your names. So y'all have a good one. Thank you for coming. Please keep an eye on my YouTube channel for other videos going up. They come at all times. And if you're looking for something specific, ask me. I'll tell you how to find them. Thanks, everybody. Okay. Charles is asking about printing and scanning. I do not mind that. I have had very negative experiences with it, specifically when students do that. They often turn in copies that are really hard to read in terms of scanning and stuff like that. So I don't mind. I'm not gonna say you can't do it. But if I get one that I can't read, I have to give you a bad grade on that. So just make sure I can see it really clearly. Uh, and feel free to do it that way. That's fine. I just try to do it with electronically so that we don't have to waste any paper. But you're perfectly fine doing it that way. You're saying print it, hand type it, all that stuff. You don't even have to hand type it. In fact, I wouldn't want you to waste time trying to put it in a typewriter and all that good stuff. I'd rather you have it just handwritten. But if
Yeah.
what you're doing is filling out the document and then printing it, make sure the font color is different than black so that I can see, even after you scan it, I can see that that color is not the same as black. So I'll know that it's something that you put in as opposed to part of the original lab.
Yeah, I was just saying because it's easier, I think, for me to print it and not type it, but write it out. And I mean, I'll be sure to be neat about it.
Yeah, that's not a problem at all, bud.
All right, thank you.
You're welcome. Have a good one.
Thank
Chloe,
you.
I
You
saw you
too.
came back. Did you have a question, ma'am?
Yeah, I just had a question about turning in the labs. Did you I noticed that there are places that we can turn them in either in the lecture part of Canvas or the lab part of Canvas. Is there a specific one that you'd prefer? Sorry.
Yeah, this class, you guys are meeting in real time for lecture, but your lab is a virtual or is a asynchronous meeting. So I
Yeah.
made an entirely different lab canvas for it. That's where I want you to turn the lab stuff in. Any
Okay.
stuff where it appears on this side, that's an accident. That's because
Okay.
I'm
Okay. All right, just making sure. Thank you.
no problem. Thanks for asking, Chloe. That was a good question.
Yep, thank you.
You're welcome, Charles. Have a good one, bud. And that looks like it. I'm not sure that that went as well as I liked it to with the Excel, but that was more a technology issue and a me prepared issue. So have a good one, everybody. Bye bye.